Okay, so unit 1 was kinematics. What do we call this unit? Dynamics. What does dynamic mean? Motion, changing, okay, something like that. So everything in this unit is supposed to be talking about changes, okay? What does the word static mean? Doesn't change, it's the opposite of dynamic. Okay, so even though we're in the dynamics unit, we do still have situations that involve static conditions. Okay? In a static condition, the object is not moving, or its velocity is not changing. Those two situations are generally governed by Newton's first law, because the net force in those situations is what? Zero. Yeah. Okay. We're talking about in a static condition situation, a situation where the net force is zero. That's why the object is static. Okay. All the forces add up to zero. Okay. And when we say all the forces, this could be vector related. Okay. The vector sum of those forces is zero. So we could be dealing with some vertical and horizontal component kind of situations. Okay, so in this situation, we have two buildings. Okay, and we have a sign that's suspended between them by two cables. So the first cable, it says, is angled 55 degrees below the horizontal. Right? So here's the horizontal. I'm going to go 55 degrees below that and draw my first cable. Okay? That's going to be attached to the sign. Okay? And we know that the sign has a mass of 35 kilograms. Okay. The second cable is horizontal and is attached to the other building. Okay, so that is 55 degrees. Okay, so this is cable 1 and this is cable 2. Other than the cables, what else is pulling on the sign? Gravity. Gravity. Okay, that's the reason we have the cables. If there wasn't any gravity, we wouldn't need the cables. The sign would just float there. Okay, so gravity is pulling down on the sign. Since I know the mass of the sign, can I calculate its weight, or the force of gravity? Okay, so I just go m times g, right? I go 35 times 9.81, and I'll get 343.35 newtons. Okay, so this is another one of those questions where there's a lot of kind of mental machinations that have to happen, a lot of things, conclusions you have to draw, and things you have to analyze in your mind, and actually very little calculating. We've done half of the calculating. So, the sign's not moving. We know the net force is zero. There's 343.35 newtons worth of gravity pulling directly downwards on the sign. What's pulling against it? Which one? Okay, so we've got two cables. Only one of them can pull up. Which one? Cable 1. Why can't cable 2 pull up? Right? It's horizontal. If it's horizontal, the only direction it can pull is horizontal. So it has no ability to offset gravity. Okay, so that's a good kind of analysis for us to make. So if cable 1 is the only one that can pull up, and it's angled, what part of it offsets gravity? because it's angled, does it pull horizontally and vertically? Okay, I know that angle. How big is that opposite side that I just drew that is its vertical component? $343.35. It has to be. It's the only thing that can pull up in this whole situation. Therefore, it has to be the thing that offsets the weight of this sign. Okay, so this side here is 343.35 newtons, because cable 2 can't help with that. Okay. Now, what else is cable 1 pulling against? Okay, the building, yep. Cable 2. Okay, cable 1 has a horizontal component as well. Remember, the sign isn't moving. It's not moving vertically. It's not moving horizontally. So the horizontal net force is 0. The vertical net force is 0. Okay, so that means that this side here is what is offsetting the pulling force provided by cable 2. If I didn't have that, the sign would go flying over into the other building. Well, and falling. It would be really bad. Okay, I need both cables in this situation. Okay, so cable A, or cable 1, sorry, offsets gravity with its vertical component and offsets cable 2 with its horizontal component. The question wants me to calculate the tension in cable 2. Can I do it? Okay. Do I know enough information about cable 1 to calculate its horizontal component? I do. I have its vertical component and I have an angle. I've got 2 parts of the triangle. Okay. Do I even need to know what the hypotenuse is in this question? I don't. I don't need to know what the tension in cable 1 is. I just need to know how much it's pulling up and how much it's pulling over. Okay. So I can find this side here because I know the opposite side, and I'm looking for the adjacent side. What trig function should I use? 10. Opposite over adjacent, right? So I'm going to say then that the tan of 55 degrees equals 343.35, the opposite side, divided by the tension in cable 2. I shouldn't write a number in there. That'll be the tension in cable 2. All right? So if I want to solve for the tension in cable 2, I'm just going to cross multiply here. Okay, so the tension in cable 2 is going to be 343.35 divided by the tan of 55. Okay, so the tension in cable 2 is, we only have 2 significant digits here, 2.4 times 10 to the 2 newtons. Okay, does that answer make sense? Like, this is a 55-degree angle, so that means this side has to be bigger than that side. So mathematically, that answer is valid. Okay, is everyone okay with that? So cable A pulls this way with 2.4 times 10 to the 2 newtons. That means the tension in B is, or in cable 2, sorry, is 2.4 times 10 to the 2 newtons. Okay, how much math did I do for that question? Two steps. I calculated the force of gravity, and then I did trig calculation. That's a 4-mark question. That's it. Because most of it is in your head. And I mean that in a good way, not the way that sounded when it came out of my mouth. It's not in your head, it's done in your head. Okay? Everyone all right with that? Okay. I forget where I was going with that. Sucks getting old. Okay, so we got 2.4 newtons pulling, oh, now I remember where I was going with that. Okay, do I put a direction on that? They asked me for the tension in cable 2. Can tension pull two ways? It can. That's why I can't put a vector on that. The way that question asked it, that's my final answer. 2.4 times 10 to the 2 newtons. That is how tense or tight that cable is. Had the question worded it differently, like this, how hard is cable 2 pulling on the sign? Then I would say 2.4 times 10 to the 2 newtons to the right. Okay, because then it's referring to, it's pulling on the sign, it's pulling the sign that way. If it asked, how hard is it pulling on the building, then I'd say it's to the left. Okay? But in this situation, it simply asked, how tight is it? Okay? That's how tight it is. Okay, did that involve a little bit of vectors? Okay, we had to do a little bit of trig there. Okay, and that's kind of where we're headed here now. We're going to be doing more things that are going to involve vectors and a lot more stuff that is more cerebral. Okay, a lot of these problems become very cerebral. That means that you're doing a lot of the stuff, a lot of the work in your head and not so much of it on paper, right? In this question, you would have got a mark for your diagram, a mark for the force of gravity, a mark for the trig calculation, and a mark for the answer, okay? But we did a lot of reasoning before we got to that. Okay? Unfortunately, that doesn't go on paper, so it's not like marks worthy. Okay, we worked on systems yesterday. This is a system question. Okay, because I'm a terrible artist, I'm going to explain my diagram so you understand what's going on in there. Okay, there is a 4 kilogram mass sitting on a table. Okay, the table is level, and there are 32 newtons worth of friction between the 4 kilogram mass and the table. The 4 kilogram mass is connected by a rope over a pulley. So this ugly thing here is a pulley, okay, to a 5 kilogram mass that is suspended above the ground. Okay, calculate the acceleration of the 5 kilogram mass. Give you a few minutes on that one. 2 forces are acting in this question. Okay, we've got the force of friction between the 4 kilogram mass and the table. Okay, so that acts that way. And what's the other force? Gravity, yeah, acting on the 5 kilogram mass. Not that there isn't gravity acting on the 4 kilogram mass, but it's unimportant because the table counteracts it. Okay? So we got a force of gravity acting on the 5 kilogram mass. That's m times g, so 5 times 9.81. You got that force there. All right, what do I do with my diagram now? Do I want to keep it like this, or can I simplify it? I can simplify it, and I have to simplify it. I don't have enough information to treat this individually, okay? So what I'm going to do then is I'm going to say, since they want the acceleration of the 5 kilogram mass, and all the masses in the system have to have the same acceleration, I can just calculate the acceleration of the system. What's the mass of the system? 9 kilograms. Okay, so here's my simplified diagram. There's the system. Here are the 2 forces acting within it. Can I calculate the net force? Okay, so I do a vector sum of all forces calculation. Okay, F net will be 49.05 minus 32, which is 17.05 newtons. All right, and that would be that way. I'm not even going to work with vectors right now, okay, because I'm going to have to mess with that later. All right, so 17.05 newtons is my net force. Can I calculate the acceleration? Okay, what do I divide by? When I calculate the acceleration, given what I just did here, I divide by 9. That's the trick. Remember I told you that yesterday, right? I might ask a question like that and specify a mass to see if anyone remembers, it's not about the individual mass, it's about the system's mass. Okay, so the acceleration is 17.05 divided by 9, which I think comes out to 1.89 or something like that. But how many sig digs do I have? 1. Okay, the acceleration of the system is 2 meters per second squared. Question wanted the acceleration of the 5 kilogram mass. What do I have to put behind that? Down. Okay, because it asked about a specific part of the system, I can indicate the vector for the 5 kilogram mass is down. And it asked for the 4 kilogram mass, I would have said forwards or along the table or towards the pulley or something along those lines. Okay? Everybody all right with that one? Okay, this question here, this is our lab next week. On Wednesday, we're going to do a lab with those carts and the tracks that we had before. We're going to put a pulley at the end of the track. We're going to connect the cart to a rope and hang some mass over the pulley. Okay? And what we're going to do is we're going to change the amount of applied force, that is how much mass we have hanging over the pulley, okay? And see what happens to the acceleration of the system, not just the cart. Okay? Of course, the cart's acceleration is the same as the system. Okay? And what we're going to do is we're going to have mass on the cart, mass over the pulley, and we're just going to keep taking mass off the cart and putting it over the pulley. Why is it important to do it that way and not just to add mass to the system? If I take mass off the cart and move it over the pulley, what do I not change? The mass of the system. The whole system's mass stays the same. I just change where the mass goes, and that allows me to get more net force by changing the location of it. But it doesn't change how much mass is being accelerated. Okay, so that's all going to have to do with exactly this situation. We're going to have the cart and its masses. We're going to have stuff hanging over the pulley. Okay? And we're going to see that as we increase the amount of force, the acceleration of the system is going to go up. Basically, we're fact-checking Newton's second law on Wednesday, okay, using this set. All right, we did one like this with the 2 blocks. It's basically the same, I just put different numbers in it. Let's see what you remember about it. Okay, so we know the total friction on the whole system is 120 newtons. The friction on the first box is 48 newtons. I want the acceleration of the 40 kilogram block and the tension in rope B. Okay. What should I calculate first here? Yeah, I should calculate the acceleration of the system first. Okay, because I'm going to need that if I'm going to calculate the tension in rope B. So, can I simplify this diagram to start off with? Should I? I should, yeah. Okay. So, my overall mass of the system is 100 kilograms. Okay. It's being pulled this way by 150 newtons worth of applied force and resisted this way by 120 newtons worth of friction. Okay, so right off the bat, I can do a vector sum of all forces question, or calculation here where I've got 150 minus 120, okay, and I get that my net force is 30 newtons right. Okay, from that, I can do an m times a calculation, and I can get the acceleration of the system, the 60 kilogram block and the 40 kilogram block. Okay, here I divide by what mass? 100. Okay, so I've got 30 newtons divided by 100 is going to give me an acceleration of 0.3 meters per second squared. Right. Right. So that takes care of the first part of that question. Calculate the acceleration of the 40 kilogram block. That is the acceleration of both blocks. Okay. Now, they want me to calculate the tension in rope B. Which box should I use? Because I obviously can't combine the system now looking for a force within it.
40.
Yeah, or
60.
I can use either one. There's an extra calculation to use 60. It's just subtraction, okay, but it's an extra calculation. All right, so I'm going to isolate just the 40 kilogram box. That's the most logical one to start with. Okay? And that doesn't mean if you did it with the 60 you did it wrong, it just means you had an extra calculation. Okay? So, the 40 kilogram block is being pulled to the right by 150 newtons. It has 48 newtons worth of friction. I'm going to call this the applied force. Okay? And then this force here is the force of tension in cable B, which is what they want me to find. Okay? So, since I know the acceleration of that block, and the mass of that block, what can I calculate? Net force acting on the 40 kilogram block. All right, so F net is going to be 40 times 0.3, which is 12, right?
Yep.
Okay, 12 newtons to the right. All right, so I know F net, and I know that for the 40 kilogram block, F net equals the applied force, 150 newtons, plus the force of friction, negative 48 newtons, plus the force tension from cable B, which I don't know, but it's what I'm looking for. So I know the other three. So I'm going to isolate the force of tension in B. Okay, I'm going to say that that equals F net minus the applied force minus the force of friction. Okay, so that's going to mean 12 newtons minus negative 48 newtons minus 150 newtons. Okay, so the tension in that rope is 90 newtons. The force it exerts on the 40 kilogram block is negative 90 newtons. But the question didn't ask that. The question asked, what's the tension in cable B? That's 90 newtons. Okay.
That'd be wrong if we added no vector.
If you put in a vector, I probably wouldn't mark it wrong. Okay, but in this case, it's not necessary, because they didn't ask how hard it was pulling on the first block or how hard it was pulling on the second block. All right, is that ringing a bell from yesterday? All right, so the system questions all work the same. We have to remember that the acceleration of the system is the same as all of the individual parts and vice versa. A 120 kilogram, I don't know if you guys have ever been to like the football games at McMahon Stadium. They got the big speaker that hangs down in the middle of the field from the four corners. Okay, so this is one that's only being suspended by 2 cables. Okay, it has a mass of 120 kilograms, suspended by 2 cables that have a 100-degree angle between them. I want you to calculate the tension in cable A. And I scrolled up right away, so you probably see that. Okay, how are we doing on this one? We want a couple more minutes? Or people are kind of stuck. Oh, and I left that recording the whole time. That's nice. Okay, what's the net force in this question? It's 0, yeah. Okay, the thing is suspended. It's not going anywhere, it's not accelerating. Okay, so the net force has to be 0, which means that all the forces have to add up to 0. So what other force is acting on this big mass that I haven't drawn on there yet? Gravity. Now, I've got force of gravity acting down. And that's going to be 1177.2 newtons, so 120 times 9.81. Okay, how much upward force is there then? The same amount. But it's being split between how many cables? 2. Now, those cables are angled, which means their tension is not half of that. It's not 588.6. Okay, not 588.6. It's something else. Okay, so each one of those cables has to support half of that. Okay, but they're angled. That force is vertical. So does that mean then that I could do this? Or maybe you drew them this way. It doesn't really matter which way you drew them. Okay? Each one of those cables has a vertical component and a horizontal component. They are, after all, angled. Okay? Since this angle was 100, that means this angle is 50. Okay? And it means that the vertical component of cable A is 588.6 newtons, half of the force of gravity, because cable B also has a vertical component of 588.6, which means there's a total of 1177.2 newtons acting up. Does everyone follow me there? The most common mistake I see is people making that side 1177.2. Forgetting that that has to be split between the two cables. And what that ends up meaning is you have a net force of 1177.2 newtons upwards, and that thing is flying up in the air. Okay, that's obviously not what's happening here. So now that I know one of the sides of cable A's triangle, and I know one of the angles within it, can I find the tension in A? I can. I have to do what? Starts with T. No, trig. I was thinking trig. I actually don't want to use tan here. I have the adjacent side, and I'm looking for the hypotenuse. I want to use cosine. All right. So, unless you do the triangle this way. If you do the triangle this way, then you got a 40-degree angle here, and you're finding it a different way. Okay. You'll use sine instead. But for this one here, the way I drew it, okay, I'm going to say that A, the hypotenuse, okay, is going to equal 588.6, the adjacent side, divided by the cos of 50. Okay, so when I do that, okay, we have 3 significant digits because the 100 also had 3. Okay, so we're looking at 916 newtons worth of tension in cable A. How much tension is in cable B? Same amount. They're identical. Okay, everything about their triangles is exactly the same. All right, how much math did we do for that? We did 3 things. We calculated the force of gravity, we divided it by 2, and then we did a trig calculation. Okay? At best, that's a 4-mark question. Sorry, 5-mark question. At best, it's a 5-mark. It's probably a 4-mark question. Okay? There's really not that much to be done there that's on paper. The rest of it is intuitive. Okay? And I have had questions like that on the Newton assignment, and I've had them on the test before. Okay? The good news is that it can be pretty quick if you can see the relationships that are in it. There's nothing that's really going to take you a long time. All right, any questions on the vector stuff? Okay, so we're kind of getting back into now this whole vector sum thing is becoming a bit more vectorish. Okay, we're going to be having to do a bit more trig and bring into account kind of things like that. We're getting some angled forces involved. All right, now we've got to look at my favorite kind, because I'm a big enough nerd that I have a favorite kind of Newton's second law question. Okay, and that is the inclined plane. Simplest machine. It allows you to make work easier. It does not make less work, that's physically impossible. Okay? But it does make the work easier. A ramp allows someone to move something they can't lift to a height. That's how the Egyptians built the pyramids. They did not have help from aliens, probably. Okay? What they did have was lots of sand to make ramps with and lots of labor. We won't say where the labor came from because where they got it from is wrong. Okay? Wasn't aliens. Slaves, unfortunately. Okay? So, we need to look at how does an inclined plane work. Okay? And we need to know that because if we don't, you will be an inclined plane wrapped around an axis. Screwed. Yeah. Okay? An inclined plane wrapped around an axis is a screw. Okay? Think about it. It's a ramp that goes around. Okay? It's a Sheldon Cooper joke, but it's good. Okay? It's not funny, but it's good. Okay. So if I put a 10-kilogram mass, like is shown here, on a ramp, and let's say that ramp is frictionless. As soon as I put the 10-kilogram mass on there, what's it going to do? It's going to slide. Slide down the ramp. Why? Okay, and the gut answer there is gravity. Yep. Does gravity pull it down the ramp? Which way does gravity pull? Straight down. This object's not moving straight down, so there's not just gravity acting here. What else is acting? Keeping in mind that in this situation, at least, the ramp is frictionless. Well, an acceleration is going to be produced, yes, because there's a net force, but there's two forces that are interacting to produce that net force. The normal force. Okay? Remember we talked about if I'm standing right here, gravity pulls me into the floor and the floor pushes back and those forces are equal, which is why I don't go anywhere, okay? Because the floor is at least reasonably level. Okay? If the floor was angled, okay, that wouldn't be the case. Right? And especially if it was frictionless, I wouldn't be able to stand on it. I would slide down. Okay? And the reason for that is normal force can only push perpendicular to the surface that's causing it. So once I incline the surface, normal force and gravity are no longer equal. Okay? They have parts that are acting in opposition to each other. So the two forces that we have on an inclined plane are gravity, okay, which acts straight down. Can we calculate what gravity is? Okay? So we just go mass times 9.81. Okay? So in this case, that's 98.1 newtons. And then we have normal force, which, as I said, acts perpendicular to the surface. Okay, so those are the two forces. That's my free body diagram. I can't get the net force from that free body diagram because they're not like collinear or anything like that, but they're both vector quantities. How would I draw those two arrows if I wanted to get their vector sum, which would be then my net force? Tail to head. Okay. So if I take this vector, and I put it right here, drawn tail to head, where do I draw my result? My resultant go here? I wanted green. Okay, would that be the resultant of those two vectors? What do you notice about this green line? What way does it point? Okay, I didn't draw it perfect, but is it pretty much parallel to the plane? Pointing down the plane? See, physics just always works. That's what makes it the greatest science. Okay, it's because it just works. Right? These two forces, when I put them and draw them as a vector diagram, they produce a net force that is exactly what that box should do. Slide down the ramp. Because that's the way the net force, the vector sum of those forces acts. It points down the ramp and that's the way the box goes. Avery, question?
Would you ever get a question where, like, with like that 10 kilogram mass, like how far that object would slide with that mass based on that angle? Like, you know what I mean?
Like how far it would slide once it got to the bottom?
Yeah, I don't know.
Yes. Maybe on your unit exam, after we've talked about conservation of energy and work energy theorem, then it will come. Not today, but it's good that you're thinking that far ahead. Okay, so that's the situation if this is frictionless, right? If it's not frictionless, okay? If there is friction, so I set it on the ramp, it's still gonna slide down the ramp, but not as quickly. Because which way is friction going to act? Up the ramp, exactly. Friction is an antagonistic force. It always works against you, right? The antagonist is always against the hero, okay? So in this case, we've got friction being an antagonistic force. If I put the 10 kilogram block on the ramp and there is friction, friction acts up the ramp because the block wants to go down the ramp, okay? So if I had friction, I would just go, all right, here's one force, here's the other force, here's friction, and my net force would still connect from there to there. It would just be smaller. Okay, because I'd bring in the vector nature of friction. We don't usually draw it that way. Okay, what we usually do is this. If there's friction, I put it there. And I put F parallel here. And then everything is collinear. Once I've taken care of gravity and normal force, all the other forces either act up the plane or down the plane. Okay? There aren't going to be any other forces that I have to worry about the vectors of other than up and down. Okay? So once I've calculated this force, which incidentally has a special name, that was angry. Okay. We call it F parallel. It's the component of force parallel to the plane. Okay? We call it F parallel. Those are supposed to be two parallel lines beside the F. Okay? F parallel. So once I've calculated that, okay, using that triangle there, okay, then I just put it on my free body diagram and I put friction up the ramp, or maybe this thing is being pulled up the ramp. Okay? Then I would have an applied force acting up the ramp. If it was being pulled up the ramp, which way would friction act? Down the ramp. Okay? Friction always opposes. Okay? So if I'm going up, friction acts down. Now, let's go back to this idea here. If I wanted to calculate F parallel, okay, what would this angle be right here? It's how much gravity and normal force are offset by. Once I incline the plane, I offset those two forces by the incline of the ramp. So this triangle in here always looks the same. Okay? This angle here is always the same as the incline angle. Gravity is always the hypotenuse of that triangle. F parallel is always the opposite side of that triangle. And normal force is always the adjacent side. Okay? So every inclined plane has the same triangle, those three things. All that's different is the angle. Okay? It's whatever the incline of the incline is. Okay, so now that I know that angle, and I know the hypotenuse, could I calculate F parallel? I could, right? It's the opposite side. Do I even need F normal to do that? I don't. we very rarely ever use the normal force side of that triangle. Okay? It's only if we're given something called the coefficient of friction, which we haven't even talked about yet, would we ever use that side. Pretty rare. Okay? So I can calculate F parallel right now using the hypotenuse and this angle to find the opposite side. So that means F parallel is going to be the sine of 30 times 98.1, my force of gravity. Okay? So that means that F parallel is 49.05 newtons. Always calculate it the same way. All right, so let's say we don't have any friction. We just want to calculate the acceleration of the box like the question originally said. Okay, I now know that F parallel is 49.05 newtons. It is the vector sum of all the forces involved in this particular question. How do I get the acceleration of the box? If F parallel is the vector sum of all the forces in this question, what is it? It's F net. Okay, that's why I drew that diagram. That was the vector sum of normal force and gravity. Therefore, it is the net force because there's no friction in this particular situation. Okay, so can I calculate the acceleration now? I just take 49.05 and divide by 10. So I've done the vector sum of all forces. Now I'm doing the m times a part. Okay, I've got two significant digits, so 4.9 meters per second squared. Down the ramp. Parenthetically. Are down and down the ramp the same direction? They are definitely not. Okay? If you have an inclined plane question and you tell me that the acceleration of the box is down, then you are telling me it is falling through the ramp. Okay? So make sure you have down the ramp and not down. Okay? All right. Yes. Okay, so we talked about if there was friction, we would have this force. It wouldn't be the net force anymore. Okay? And friction would act up the ramp like so. What if the situation was I'm pushing the ramp, or pushing the box up the ramp instead? So now I've got an applied force, let's say, that is, I don't know, 70 newtons. Okay, now which way is the box going? Up the ramp. I got 49.05 newtons down the ramp, I got 70 newtons up the ramp. If there's no friction, this thing is flying up the ramp. Okay, because the net force is now up the ramp by 20.95 newtons. Okay. If there was friction in this situation, which way would it point? Down the ramp. Remember, friction is an antagonistic force. If your box is moving up the ramp, friction is acting down the ramp. Okay? Friction always acts opposite the direction of the motion. Okay. All right, questions on that? Okay. If you don't have this diagram, especially the heart of the diagram, okay, that would be that internal triangle, have it copied down. You're going to need it. It's always the same other than the angle. Okay? F normal is always the adjacent side. Okay? FG is always the hypotenuse. F parallel is always the opposite side. Okay. I would like you guys to try on from your digital workbook. There's a page called Inclined Planes Worksheet, right? And I would like you guys to try 1, 2, and 3. Okay, 1 is like the first one we did. 2 has some friction in it. Okay, 3, well, the important words are in bold. All right, so on number 2, we've got our hill, icy hill, that's angled at 20 degrees, okay, above the horizontal, and we've got our 2,000 kilogram truck, okay, sitting on it, right? The forces acting on the truck, obviously gravity, which is acting down, okay, which will be 19,620 newtons. Okay, normal force here, which won't be required for our purposes in this question, and F parallel, which will be. Okay, the angle inside this triangle is 20 degrees. The other thing they tell us is that the force of friction is present, and because the truck is going down the hill, the force of friction must be up the hill. Okay, so we could also say then that that's F parallel. Okay, can I calculate F parallel right now? Yeah, I can. Okay, I just got to do a little bit of trig. All right, so F parallel, as it's always going to be, okay, is going to be the sine of the angle of incline times the hypotenuse of that triangle, or the force of gravity, 19,620 newtons. Okay, so we're looking at 6,710 newtons down the ramp. Okay, so 6,710 newtons. Okay, do I need the force of gravity anymore? Now I'm just dealing with up the ramp and down the ramp. I used the force of gravity to find the amount of force down the ramp, and now I'm done with it. Okay, so now I'm going to find the net force. How will I do that? What do I do with these two forces? Vector sum, right? This is the vector. I've already done part of the vector sum. Now I'm going to do this part of the vector sum. So F net is going to be 6,710 newtons down the ramp minus 500 newtons up the ramp. Okay, that's going to give me 6,210 newtons down the ramp as my net force. Can I get the acceleration now? 6,210 divided by 2,000 should give me that 3.11 meters per second squared down the ramp, or down the hill, I guess we should say in this situation, it's down the hill. Okay. All right, everybody okay with that one? Okay. Did I still end up doing those two things I said you'd do in every problem? I did. It's just the vector sum of all forces part becomes more and more convoluted as we go along. Okay, but we're always going to do that and m times a, which is what we did here. Now, something that can happen sometimes is a question, instead of giving you the mass, will tell you the truck is this many newtons. What are they telling you if they tell you that? They're not telling you it's mass, they're telling you it's weight, which is which force? Weight is the force of gravity. So if a question ever says, you got a box that's 20 newtons, it's not 20 kilograms, they're telling you the force of gravity is 20 newtons. So they're probably saving you some work because they're telling you that side of the triangle is 20 newtons. Okay, just be on the lookout for it because it happens and it's easily confused. Okay, how many people have done number 3? Are we ready to go over that one, or do we want a couple more minutes? I'm going to give you a couple more minutes because I don't think everybody's on it yet. Okay? We might not get to it before the end of class. Okay, we probably won't get this one done before the bell goes, but what's the most important part of this question? Constant velocity. What does that mean about the net force? It's 0. So that means the forces acting up the ramp and the forces acting down the ramp are equal. Okay? So if they're looking for how much force is going to be required to push these rocks up the ramp, okay, that would be the applied force. Well, then that's going to equal the sum of the two forces acting down the ramp, which we should be able to calculate. In fact, we're given friction. They say it's 800 newtons. Okay, so we should be able to figure out what F parallel is, and then they add together so that your net force is 0. Right? Okay, so we're working on some more stuff to do with vectored forces tomorrow for sure. Okay, and then next week, obviously you got Monday off, nice for you. Okay, and then coming back on Tuesday, some more Newton's second law. Wednesday doing a lab.
That was only 3 sick days.
I know, I changed it, actually.
Okay.
I changed it in my document, it won't be changed in yours.
No.
But good eye to catch that.
What's on?
It'll be some.